Hi everyone, I'm Anish and welcome to PrepFusion. So this is the lecture 4 for the state space chapter basically. So like the previous lecture we were going to solve questions, but as it got extended more than 1 hour, so I stopped there. Also I was feeling a bit sleepy. So yeah. So in the previous lecture what we learned about the state space representation, how we represent the state equation and the output equation, how we write those things, and what are the matrix form, and what are the basic names of those matrices, right, and the vectors. Okay, and what will be the order of each matrices and why will the order be like that. Okay, all those things I explained to you in a very detailed manner. Okay, so now we'll start the lecture 4. We'll solve the questions with the state space representation. So this is the first question. The first question, what is it asking us to find is, find the state equation of the system from state diagram. So we have been given the state diagram. We have to find the state equation of the system. Okay, then where it is telling where y of t is the output and u of t is the input. So not the state equation, also the output equation also. So I should write here is state equation and output equation of the system. Okay, so yeah, this is basically the basically the question, right? So what we'll do, we'll follow the simple steps that I told you in the earlier examples, right? So how to solve for the state equation from state diagram. So what we'll do, we'll remove the we'll write the terms in time domain. Okay, also we'll remove the 1 by s terms. Also we'll remove the initial conditions also. Okay, and we'll take into effect of 1 by s with respect to differentiation. So all this I will do in a single step only. Okay, to that's how you should do in exam. Okay, I solve it in very thorough manner in the first few lectures. Now I will solve it bit quickly to explain it to you how you should solve an exam when you are very accustomed to this procedure. So just what I will do, things that I need to do is, remove the initial conditions. Okay, remove the initial conditions, then remove the write the time domain expression, write time domain expression, and what we have to remove the 1 by s terms, right? Remove 1 by s paths. Okay, so this is what basically we have to do. So now firstly remove this one initial terms, right, initial conditions. Okay, then what we have to do, simply remove the 1 by s. Before that I will write the x1 x2. So this is x1, right? This is x1 already written in the question. So this is x2. So here this is x2. Let me write it here. This is x2 of t. Let me write this as x2 of t. This, let me write this as x1 of t. Okay, this as x2 of t, and let me write this equals to what will be this? This will be the differentiation of the x1, right? x1 of t. So this will be x1 dot of t. x2 of t will be equals to x1 dot of t. So remove this. Okay, not like this. I will remove this 1 by s term. Okay, and I will remove this 1 by s term also. Okay, and what will this be? This will be x2 dot of t. Okay, I will okay, as we have 3 1 by s, right, we will have 3 state variables. So this will be x2 dot of t, which will be equals to x3 of t, right? So x3 of t equals to x2. Okay, this is getting less space. This is equals to x2 dot of t, x2 dot of t. Okay, Now again I will remove this 1 bias term, and this becomes x3 dot of t. This becomes x3 dot of t. Okay, so yeah, this is basically the time domain expressions, and we have removed the x terms. Okay, now what we will do, we will simply write the state space equations and the output equation. So from here itself I can see that only one node is leaving from x1. Okay, only one path there is from x1 to y, right? This is y of t, actually this is y of t, and this is e of t. So we have only one path from x1 to y of t, right? And we have that's why what will be y of t equals to, y of t will be equals to x1 of t, x1 of t. Okay, now this is the output equation. So this is the simple output equation we got. Okay, now let's solve for the basically okay, wait, I have some work to do, just hold on a second. So sorry for the disturbance, actually someone came in door. So yeah, this was the output equation. So now let's solve for the state equations, right? So what is x1 of dot t equals to? So as I can see, x1 of dot t, right, this one is x1 of dot t, is like anything else coming other than this x2 t equals to x1 dot t, right? No, nothing is coming. So simply we have only one equation, but we will have problems when this x1 t, right, when this x1 t has multiple paths. If this x1 t is also interconnected with this like x1 dot of t, then we will have an issue. So we will solve this issue in the next question. So now I can simply just write that x2 equals to x1 dot of t. That is very simple. But in the next question we will see what will be our problem if I simply write like this. Okay, so this is x1 dot of t equals to x2t equals to x2t. Okay, so again this is again I can simply write x2 dot of t equals to x3t, right, as nothing else is incoming. So x3 dot of t equals to x2 dot of t, sorry, x2 dot of t equals to x3 of t. Okay, and now what, like now what is x3 dot of t equals to? What is x3 dot of t equals to? So x3, right, it has these three paths, right, only simply these three paths, and they are only connected like this. Also it has input also, so I can simply write it in addition. Okay, simply write it in addition because these doesn't have any other input parts, right? If this x2 dot also had this interconnected, then I wouldn't have been able to write this simply. Then what I would have had to do, I will explain it to you in the next question. So this is x3 dot of t, which is equals to simply u of t. U of t is, I will write it later. First I will write the state variables. So first I will write the first state variable, which is x1 of t into minus 1. So minus x1 of t. Then this is the second state variable, that is x2 of t into minus 3 into x2 of 3 x2 of t, and this is x3 of t into minus 2. So minus 2 into x3 of t. Okay, now what we are adding? We are adding u of t with this. So we have also the input 1 times u of t, which is u of t itself. So these are my state equations, and this is the output equation. So this is my state equation basically. Okay, this is my state equation. So yeah, Now, like, let me write this in matrix form. So in matrix form, how will they look? Simply, I will just copy this, right? I'll just copy this and I will delete a few. So here we'll have a column vector of x1 dot, x2 dot and x3 dot. Okay, so these three will come in together. Okay, for me it's just a copy and paste. Also I have to move things around, but for you have to rewrite it again. So this is x1 dot t, okay, and we'll have only one equals to, and like what are the coefficients of all this. So here I will just put this down below, okay, for my reference. So what will be my A matrix this time? I hope you understand why this is a 3 cross 3 matrix, okay, and what is the A matrix, what is the B matrix, what is the C matrix, all these things. Why B matrix will be a simply 3 cross 1 matrix, as we have only one input. Also why the C matrix will be a 1 cross 3 matrix, as we have only one output. Okay, so what will be like the first row? 0 1 0, as x1 dot equals to x2 only. So this will be 0 1 0. Now the second row will be 0 0 1, as x2 dot equals to x3 only. And the fourth row will be this, we have minus x1 minus 3x2 minus 2x3, and this is the our matrix, and this is the our state vector, that is x1 of t, x2 of t, x3 of t. Okay, and we have the input also. So the like only x3 dot t is like dependent on the input, so others will be 0 0 1, okay, and this is u, this is u. Okay, so yeah, this is basically the form, state equation form, matrix form. Also let me write the output form also. So the output form, right, this will be y of t basically. Okay, this I can write as u of t for better understanding. Okay, now the output matrix will be a row matrix, and what will it be? It is like y equals to only x1, y equals to only x1, so it is only depending on the first state variable. So we'll have something like this, 1 0 0, and again the state vector x1 of t, x2 of t and x3 of t. Okay, and do we have the d? What is the value of the d? D is a null matrix. Why? Because y is not directly dependent with the input, it is related with the only the state variable. That's why d in this case is 0, and in most cases d is 0. Okay, but obviously don't take it for granted. In some cases d may come non-zero. Okay, so what I was talking about by the like the problem, right? Problem of writing equations like this, So problem. So what will be my problem? So if we had multiple paths from x1 to x3. Okay, if you had multiple paths, by that what do you mean? So let's say like this was my state diagram, right? I had here x1, then here I had some other like this was x3, this was x3, this was x2, x2 dot, and this was x1 dot. Okay, and this is x1, and this is my output. This was my output, right? This is 1, this is y of t. Okay, this one was my x1 of t. Now what is happening? Instead of these being isolated, right, we have a interconnection between these two, right? Whatever the gain is, okay. Also we know that this is also connected with this one also. Okay, and this is what, this is the x2 of t, and this is the x3 of t, and this x3 of t is also connected with this one. Okay, and this is also connected, right? So what I am saying, this x1, right, is going from here also and here also. So only writing this won't cut it, right? Only writing this won't cut it. Okay, also for like if these if this x3, right, is connected with x2 like this, okay, whatever the gain is, I don't care about the gain right now. So then there will be issue. I just can't simply write the value of x3 in terms of these three path gains, right, multiply with this. So we have to use Mason's gain formula. Okay, we have to use Mason's gain formula. So for solving this, so that is the like a main catch that we have to take in mind. So in the next question we'll exactly do the same. So this is the next question that I was talking about. So here what you can observe is we have multiple paths, right? Multiple paths like this one, and like something is going here, then I can go from here also. Okay, this is also a path, so this is also a path. So yeah, that is what we need to take care of. Okay, so for this question we'll solve this very carefully. So first thing what I will do, I will copy this state diagram. I will copy this state diagram basically. So now what I will do is, so here obviously I will remove the initial conditions. So okay, again removing the initial conditions. Also, right, I will write the x, we have three 1 by s terms. I will write the x3 where I have the last 1 by s, just after the last 1 by s. Okay, this is the last 1 by s, like just near the input. So just after this I will write my x3. Okay, so that I can get x3 s into x3 here. So I will write here x3 of s. So this is s into x3 of s. Okay, s into x3 of s. So yeah, this is what x3 is. So now what I will do is simply now solve this, right? Simply now solve this. So what will be my this is my x1 of s, this is my x1 of s. So what will be this? This will be s times s2 s times x1 of s, which will be equals to simply x2, right? So this is s times x2 of s, which is simply equals to sorry, this is x1. Simply equals to x1 of s. Okay, so yeah, this is what we get, right? This is what we get. Okay, so sorry, this is again I'm just confused. This is x2. So defining x2, x1, all those things is very important, right? All those things is very important. Just be careful. Just where this 1 by s term is, just after that there will be a state variable. Okay, that's the convention that we follow in this method. For this particular method, that is the convention that we are following. Okay, so just keep in mind the convention that we follow for this particular method of finding the state equations, right? So convention what we follow, where the 1 by s term is, just after that is the state variable, just before that is s times that, and obviously the other state variable. So now let me write the time domain expression for this. So also write let me write here what I did, right? Just after 1 by s. Okay, just after one pass. Okay, so yeah, this is what I did. Now let's write the time domain expression. Let me copy this. Okay, also like I will remove the one base terms also. YFT. Okay, YFT. So what is this equals to? This is YFT. Now this is again, this one is x1 of t, x1 of t, and this is x1 dot of t, which is equals to x2 of t, right? And like one more thing here, this is x2 dot of t. Okay, but is this equals to x3 of t? Is this equals to x3 of 3? So I can't say. Why? Because it has multiple paths incoming, right? Multiple paths incoming, that's why. But this was just x1 of t and this came here, and that is fine. But is this equals to x3 of t? No, x3 is here only. X3 is here only, just after the state variable, right? Just after the state variable. So yeah, that is one important point to note. Because this x2 was here only, because just after the state variable we have x2, but just after this let's not state variable, state path, right? 1 by s term. Just after this 1 by s term I have x3. Just after this 1 by s term I have x2. Just after this 1 by s term I have x1. Okay, so here this is not equals to x3. Just be careful about that. So I will write the x3 here, not equals to x3 here. Okay, so this will be x3, and this is x3 dot of t. Okay, this is x3 dot of t simply. So now what I will do, I will remove the 1 by s terms. Remove the 1 by s terms. Okay, so I'm left with this. So what I can observe is that this this x2, right? This x2 has also multiple paths. How? Like this x1 can come from here also, this x1 can come from here also. Okay, so this has multiple paths, right? So yeah, that is one important thing to note here is. So now let's calculate the value of x1 dot, x2 dot and x3 dot in terms of other state variables and the output, right? So firstly, again the output equation won't change. Output equation will remain same. Okay, output equation will remain same because this output, right, doesn't have any other forward path. Okay, this has okay, this has this x3 also. So yeah, this output equation may change. This output equation also may change. So you have to see, does other forward paths come to this output, right? That is what you have to observe. So I will solve this question. From there you will understand in a better manner. So the simplest equation is this x1 dot equals to x2. That is the simplest equation. So we'll write x1 dot equals to x2 dot. Okay, now what is the another equation? What is the another equation? x2 dot t. What is this equals to? For this we have to use the Mason's gain formula. Mason's gain formula. Like this one was easy, right? Only one equation, as this doesn't have any other incoming nodes. This doesn't have any other incoming nodes. Okay, okay, because I can come from here. Okay, because this is the opposite of the flow direction. So this has only this equation. Now for this x2 dot, right, this has 3 incoming nodes. So this x2 is coming from here, this x1 is coming from here also. Okay, and this x3 also coming. Okay, so we will have to use the Mason's gain formula. So what I will do, first I will find for x1 of t. So what it will be equals to, so I will make other input 0, right? So that's how I use the SFG, right? I will make this all the state variables when I'm calculating the ratio of x2 dot upon x1 dot, I will make the other state variable 0 and then combine them using superposition. We did one question at the end in the SFG chapter. I hope you remember that, right? So I will make the other input 0. So what I will do, I will write x2 upon x1, right? Sorry, x2 dot upon x1. So how many forward paths we have? So one forward path I can see is this one, right? This is one forward path, right? So this is 1 times minus 2. Okay, so 1 times minus 2, and any other forward path we have. So this is simply again another forward path we have is this one, right? Another forward path we have is this one. So we have 1 times minus 1 times 1. So we are reaching x2 again, but for that I have to find the associated loop factor for the previous forward path. So how many loops do we have? So in the whole SFG, right? So like I have, you are already pro at this, but still I'm doing it slowly for you. So I think this one, right? This one, no, this one isn't a loop, but this one, yeah, this one is a loop, right? This one is a loop. Okay, any other loops we have? No, this one is like floating, this one is also floating, so this can't be a loop. So we have only one loop this time. Now when I'm traveling from here to here, okay, anyways this node is common, so this loop won't come in action. So again our associated loop gain will be 1 only. So this will be 1 minus 0. Okay, and this is what is the other? This one was minus 1, right? 1 times minus 1 times 1. Okay, and then 1 here. So this is minus 1. Again this node is common, so it will be again the associated loop gain will be 1. So what do we have in the denominator? It is the determinant, right? It is the determinant. So the determinant, this will be simply the value of the loop gain, right? 1 minus the loop gain. So this is minus 3 times 1 times minus 1, right? So this is the this is basically the loop gain, right? So this is simply equals to 1 minus 3. Okay, I'm going from here, times 1 times minus 1. So this is times minus 1 basically. So this becomes, okay, this is times minus 1. The upper half becomes minus 2 plus minus 1. So this is upper half becomes minus 3, and the bottom half becomes, this is minus minus plus. So this is minus 3, sorry, this is plus 3 minus, and 1 minus 3, which is minus 2. So this is simply 3 by 2, right? This is simply 3 by 2. So this is how you can solve this question, right? So this becomes 3 by 2. Now like what I can write is x2 dot of t equals to 3 by 2 of x1 of t when other variables are 0. Variables are 0, right? When other variables are 0. So now again, like what I should do is find the ratio of x2 dot of t with respect to x2 itself. So let me write this. So what is this? So like here what I can see is only like this x2, right? x2 dot of t, only this x2 is incoming, right? Nothing else is incoming. But still, not to take any other risk, I can simply write this x2 dot of t equals to x2 itself when other sources are 0. But still, not to take any risks, what I will do, I will simply write the SFG Mason's formula. So again, how many forward paths we have? We have only this forward path, right? We have only this forward path. So again, this time, is it touching the loop? No, because the loop is going from here to here, right? And the path is here. So what we will do, simply we will write the loop gain in both numerator and denominator, and they will get cancelled out, right? So that's why I could have simply written x2 dot equals x2, but still we shouldn't take any risk. There may be a surprise factor or some forward path that is reaching x2 dot, right? So it is very risky. So use the Mason-Dixon formula for you to be safe when there are loops and multiple forward paths coming to that state variable, right? So as you solve questions, you will understand better more. So the loop gain is -1 only, not loop gain, the forward path gain. This is -1, and what is the loop gain? Like the previous one, right? So this is 1 minus this one, right? -3 into -1. So this is -3 into -1, and this is 1 minus -3 into -1. Okay, so what is this equals to? So this numerator and denominator gets cancelled. We're only left with -1. So x2 dot equals to minus of x2 of t. x2 dot equals to minus of x2 of t. Okay, so this is what our x2 dot is. Now let's solve for the third equation with respect to x3, right? So x3, so what I will write is x2 dot, okay, let me use different color. So x2 of t by x3 of t will be this. Now again, what are the forward paths? Again, what I see is, like from x3, right, I have only one forward path, none anything else I don't have. Okay, because yeah, this forward path, this is also another forward path. Yeah, okay, then this is risky, so I won't be able to write simple this equation. Okay, we have multiple forward paths, so I will use the Mason-Dixon formula again. So always use the Mason-Dixon formula anyways. So again, the first forward path is this one simply only. Again, this is breaking, like this is common with the loop, so we won't have the associated loop gain, will be 1. What is the forward path gain? This is 1. So 1 times the associated loop gain, which is 1 only, then plus what is the other forward path? So the other forward path is like this, right? I'm going like this. So the loop gain, what is the forward path gain? It is 1 times -3 times -2, which is equals to x2 dot. So this is this is equal to 6, right? This is equals to 6 only. So I write this like this: -3 into -2. This is 1 minus 0. Okay, and what is the x3? Like what is the determinant? Again, the loop gain, right? So simply 1 minus -3 into -1. Okay, I have to remember. So this is again in the denominator we have again 2. Okay, -2, and in the numerator what do you have? 1. This is plus 6. So this is 7 by 2. So what is my answer? My answer is minus 3.5. So x2 dot of t equals to minus 3.5 x3 of t. Okay, now can I is there u of t in this relation? So what I can see, no, there is no forward path gain for u of t. So forward path gain for u of t is 0, right, for reaching to x2 dot of t. So yeah, u of t won't be present. Okay, so yeah, this is now let me write the full equation for x2 dot of t. As I am explaining it to you, so this may look like slow, but you will do it very fast, because solving the SFG for this is very easy for you. Okay, as we have many floating nodes. Okay, so we will the signal flow graph will be very simplified. So x2 dot of t will be equals to this first one, that is 3 by 2 x1 dot of t, which is 1.5 x1 of t, and this is simply minus of x2 of t, and this one is minus of 3.5 x3 of t, minus of 3.5 x3 of t, right, minus of 3.5 x3 of t. So yeah, this is what x2 dot of t is equals to. Okay, now let's solve for x3 dot of t. So for x3 dot of t, like what do you have? What do you have for x3, right? We have only the input because none of them are coming for the forward path. Okay, there isn't any interconnection for x3 dot of t. So x3 dot of t is simply equals to u of t only, because we don't have a connection. This node is floating. Okay, so x3 dot of t equals to u of t only. Okay, so just be careful about this. Now let us write a matrix format for this. So matrix format, so this one will be, again I will copy this only. Okay, and I will just replace the values. Okay, I will write the output equation later. So what will be this? So again, what is x1 dot of t equals to? So x1 dot of t is equals to x2 of t only, x2 of t only. So again this will be 0 1 0, this will be 0 1 0. Now what will be like x2 dot of t, that we just solve this equation, right? So this is minus 1.5 minus 1 and minus 3.5. So 1.5 minus 1 and minus 3.5. okay, so this is my simply x2 dot of t. Now what is my x3 dot of t? It is not related with any of the state variables, so this row will be whole 0, right? So what are the repercussions of this, we will understand now. U of t, none of the state variables are related with u of t except the third one. Okay, that is the state transition variables. So third one is related with the u of t, right? So this is one. So now let's solve for the output equation. Let me again bring the SFG. Okay, for again we have to use the Mason's formula, as we have multiple forward paths, right? Multiple forward paths. So calculation of output equation. Okay, calculation of output equation. So now how many forward paths we have? We have this forward path, right, for the output, and also this x1, right? This is also incoming. X2 is not. So y of t will be related with x1 and this x3. So related with x1 of t and x3 of t. Okay, so again I will do the same procedure again, follow the same procedure again. So y of t by x1 of t, what will it be equals to? It will be equals to simply so x1 of t, right? So how many forward paths it has? It has only one. Okay, I can't go from x1 to y of t with any other forward path. So what is the gain? 1 times 1 times 1, which is 1 only. So this is equals to 1 only. Okay, and what is the associated loop gain? Again this node is common for this one single loop, right? So again this associated loop gain will be 1 only. So 1 minus 0. Okay, and what is this what is this determinant? Again the loop, right? So it is like same only. So 1 minus 3 into minus 1. Okay, which will be equals to simply minus 1 by 2. Denominator we have minus 2, so this is minus 1 by 2. So again y of t equals to minus 1 by 2 x1 of t. Okay, here I should write also this step, right? This step came by applying superposition. So I hope you are understanding if I'm not writing everything. So applying superposition, right? Applying superposition. So yeah, here this is like the relation between y and x1. Now let's find the relation between y and x2, sorry, x3, y of t upon x3 of t. Okay, so again, how many forward paths we have? So what I can observe is only this is the forward path, right? So I can go from here, this is against the flow. I can go from here, but from here I don't have any path because this is also against the flow. So only we have this forward path. So what is the gain of that path? This is 1 times minus 3, 1 times 1. So this becomes 1 times minus 3, 1 times 1, so which is 1 only. Again, as we can see, this is taking into action the loop only. So again, the associated loop gain will be 1 only. Now what is the determinant? So 1 minus minus 3 into minus 1 again, the same thing, right? So what is this equals to? This is minus 3 by minus 2, this is 1.5 only. Okay, so what is y of t equals to? Y of t equals to 1.5 x3 of t. Okay, so yeah, this was basically the values. So let me write total again by applying superposition. Applying superposition, what do I get? Y of t equals to minus 0.5 x1 of t plus 1.5 x3 of t, right? Plus 1.5 x3 of t. This is what y of t equals to. Now let me write this in matrix format. So the matrix form basically, okay, what will be the matrix form? So matrix form, right? Again, this will be y of t only. This will be a 1 cross 1 matrix, okay, because we have only a single output. So this will become, it is related with x1 of t, not related with x2 of t, and also related with x3 of t. Here we have x1 of t, x2 of t, and x3 of t. Also it is not related with the input, right? So D matrix is 0 only. Okay, D matrix is null matrix only. So yeah, this is how like my output equation will look like in matrix format. Okay, so like this was a solution for this question. So at this lecture, what you have to keep in mind is the main thing is you can't just simply write the state equation here. Okay, you can't simply write the state equation here that x1 x2 dot of t equals to only x1. Okay, you can't do that because we have other forward path also, like this one, right? It is related with x1 also. Okay, this one is related with x1 also. So you have to take care of all those things. So for that, just to be on the safer side, what you will do is you will use the SFG. You will make other state variables 0 while finding the relation between this state variable with respect to the output. Okay, just as we did in one of the examples in our signal flow graph chapter. So that is what the main crux of this lecture is. These things you have to keep in mind, how to solve when we have multiple forward paths incoming at the output node. Okay, multiple forward paths from different state variables incoming at the output node. Okay, and they are interrelated to each other. So yeah, this was the main thing, how to solve that. Okay, just using SFG. So SFG, I hope you have got enough grip and enough practice with SFG, so it won't be an issue for you, right? So yeah, that is it for this lecture. So in the next lecture, we will do the solution of state space equation, how to do the solution and few more questions, right? So yeah, thank you for watching.